All right, hello everybody. Welcome here. Good to have all of you here tonight for my talk in partnership with the University of Manitoba IEEE chapter on printed circuit board design with Altium. My name is Jack Oshway. I am a fifth-year electrical engineering student here at the U of M, and I'm on the UMIEEE Formula Electric team, as you can see. I am the electrical systems officer, and I have about 4 years of PCB design experience there on the team, and I'm happy to be here tonight and hosting this for all of us to learn a little bit more together. So I think what I'm going to do tonight is we're going to be building a circuit board together. I don't know if you, hopefully you got my email earlier this morning about downloading Altium. If you do have Altium, open it up now and you can follow along with me as we do this together. There's nothing that I will do that you can't do on Altium. You most likely can follow along everything that I'm doing on Eagle as well. And even though it's going to be a little bit different, or any other PCB design software, there's a lot of stuff that I'm going to be talking about that is I'm going to be demonstrating with Altium, but is going to be relevant to any PCB design software that you choose to use. They're all quite similar. Some have their differences, but at the end of the day, you all get a PCB with whatever software you choose. So I'm going to be starting with this presentation here and going back and forth a little bit. My fan on my computer likes to act up when I have my camera on, so I think I'll turn my camera off when we get started here, and just so it's a little bit easier for you guys to listen. And this is being recorded, not through Teams, but I have it going here through OBS on the side. So Brendan and I will find a way to distribute a recording or make it available through IEEE somehow so you can do this after. But you should be able to follow along. Let me know if there's any trouble with opening Altium at any point, or any other problems with Altium. Please feel free to jump in anytime with questions. Put them in the chat. Unmute yourself. I'm more than happy to be interrupted and to stop and answer your questions. Way better to sort something out if you have an issue while you're doing it, and then wait to the end. And then there definitely be some question time at the end, and I can cover some more advanced topics or something else that anything else that you guys have interested in. So with that, I'll turn off my camera and we'll get started. So the PCB design process, and this is again relevant to any schematic editor or PCB editor software that you're going to use, but you're firstly going to create your circuit schematic in the schematic editor, similar to what you would do in Multisim or LTSpice or another simulation software. You're going to import your components after you've made your schematic to the PCB editor, the physical representation of your design. You're going to place the components on the board, route your traces, generate the design files, and send them off for manufacturing. That could be to somewhere here in North America or around the world, and solder your components to the board. And you're going to be going back and forth through this multiple times. Like even tonight, I'm sure we might go back and forth a little bit, even we're doing a somewhat simple circuit. Definitely for a larger board, more complex, let's say you're doing a board with definitely like a microprocessor or something else that's pretty hands-on in terms of the design, lots of stuff going on. You're going to be going back and forth as you're laying out the board to not even just big changes to your design that are outside of the board, but changing around where pins are located on your schematics, changing maybe you got the footprint wrong of something, and you go back and forth through this all the time. Hopefully, at the end of the day, you don't have to go back from step 6 here all the way to step 1. That's not great. That's called revving your board once again, although that does happen once or twice, if maybe in a design. But you try to make that not as big of a situation, because of course going from step 4 here back to step 1, there's no cost involved in that. Once you've sent your off to manufacturing, ordered all your components, and soldered them on the board, now you've sunk cost into your project, and you probably don't want to do that. So be wasting your money on ordering a bunch of PCBs. So you want to make sure that it runs right the first time, and that's done at before even you get to the schematic design process here by simulation. And If you're on the UMIEEE team and Formula Electric, anybody here from there, you'll know what I'm talking about. You've hopefully done some simulation, circuit simulation at some point. And that's the first step, even before we get to anything I'm going to talk about today, is before you put something on a PCB or even lay it out in the PCB editor, you want to make sure that it works. That the way to do that is through simulation. You can simulate stuff through Altium, although I've never done that, so I'm not going to be covering that today, although there's definitely lots of resources online for that you can do for doing circuit simulation in Altium. So what we're going to be simulating today, or not simulating rather, but laying out on our PCB is this circuit here. Has a NE555 timer, very common timer that is used for it can be used for a whole bunch of stuff. Today we're going to be using it, I believe, what's called the astable mode, and it's set up here with a couple resistors and this capacitor, and that actually acts as to trigger the ADC. The output pin here is going to be cycling up and down, kind of in a square wave function, giving an output between VCC and ground. That output is going to act as the clock input for this CD4017 counter. Also a fairly common device. And it's going to be, on each clock pulse, going to be counting up in a binary fashion on these pins here. And you're going to get different LED outputs as you count up on these pins here. And then when the carry happens, depending on when you get to the top of your count for this 10-bit output here, you're going to get a red LED. And then the green LED and the yellow LED is going to come on at various points. These diodes here, this D11 here is it's a little bit unnecessary, but these three diodes here, 5, 6, and 9, are for making sure there's no current that flows back into the counter here. So I'll point out a few points here on this schematic even before we get going. You'll see that very similar to multi-sim, right? Every component has wires connecting it. Every component has a designator that uniquely specifies the component, and that's something that's very much necessary when you have a PCB maybe with 300 or 400 different components on it. You need to be able to identify each of those components individually. So anyways, we'll get back to the presentation here. So first thing you need to do in Altium or in any PCB software is you have to create a new project. And each PCB project is going to contain at least 2 separate files, one for the schematic and one for the PCB document itself. For Altium, these are .schdoc and s.pcbdoc. That's the file extensions. For this project here, I have 7 schematic documents and 2 PCB documents. One of them was my first rev of the board, V0, and then the V1 was the second revision. We didn't actually order from 0 to 1. In this case, we just changed it for space and size purposes. Change it around. And this specific board, I'll actually show you a few things from it throughout the evening about different PCB design features. There's a couple other files, PCB and schematic libraries, and I'll be talking about those a little bit later. Then there are other types of files even beyond that can be added to your project. So first thing we'll do here is come into Altium and we'll create the project. So what you want to do, we have Altium open. These are 2 other projects I got open here, but again, we'll come to those later. File, and come down to new project, and PCB or multi-board project is what it shows you. There's also different Altium 365 and version control locations that you can select from. This is if you have a repository such as GitHub, and Altium 365 is Altium's version of version control for specifically PCB projects and other types of Altium projects, but that is something that I won't cover tonight. But it is, I know from other experience from other people, it's pretty slick using that Altium 365. But anyways, we're just going to be storing in our computer for today. And we'll call this UMIEEE tutorial. And the parameters, don't have to worry about that right now. We'll create. creates the project, and you'll see that there's one beginning here, no document. So you want to right click on the project, add new to project. You can also add an existing schematic document to a project. So if you have a friend who's already done a schematic, or you have a schematic from a different project, or found something online, or whatever, you want to add that to your project, this is how you would do it. But if you want to add a new schematic, you can just go add new to project and add schematic. As you can see, there's a bunch of other stuff that you can add as well, and I'll go over some of this later. But for now, we're going to go add schematic. And so this is the schematic sheet. You can change the size of this sheet. This is an A4 sheet. Generally, you should try to keep all the schematics on the same sheet size if you have multiple schematics in your design, because this allows you to, for example, print them off easily all on the same size, like 8.5 by 11 piece of paper if you want that. Obviously, if the only thing you're going to do is export it to a PDF, and that's not that bad, but to have different sizes. But generally, if you have so much schematics on one sheet, then take half of them off, put them on another sheet, and that makes it just easier on your eyes when you're reading the sheets, and to make it a little bit more organized. So we're going to go back now to the PowerPoint. Okay, now that we have our schematic sheet, just a blank piece of paper, now we have to place components. And we can take those components from generally four different places. Every component that you have to place on your schematic is going to have a footprint associated with it. A footprint is the physical, I'll talk about them in a second here, but the footprint is the physical pads and through holes that are going to be placed on your physical circuit board that's where you solder on your components. So the best and easiest place to take your components from is Altium's built-in libraries. And that has the most simplest components, resistors of a few different types, capacitors, diodes, lots of different header connectors. You've probably seen those ones that you might get on like a Arduino or a Raspberry Pi board. Those kind of just the ones with the black plastic on the bottom, those little pins. And they're easy to use and free, built right in. And you can change the footprint if you want as well, which is important depending on you use the symbol that they give you, but you can get the footprint from somewhere else and change it out. Manufacturer part search is the next level up, and that is one of my favorite features of Altium. Is for thousands of different components, Altium has also the libraries kind of built in, slightly different than their just the simple ones, but it also has those libraries built in for you to use, and I'll show you how to use those in a second, because we'll use those libraries to bring in our NE555 timer and counter, and you'll see just how easy it is. The third thing you can do is you can download it from an online source such as Ultra Librarian or EasyEDA. There's a number of different ones that you can places online you can Google it from. I know for some suppliers, I think Mouser has this, and I think DigiKey does too. You can actually, it's really built in right to their site. You can download the footprint. It's kind of linked through the site for many components. You can download the footprint right from there, which makes your design easier. If you're going to be searching for parts in DigiKey, and then you're going to want to right from there, copy and paste the part number to Google to get the schematic and the component footprint, but it makes it a step easier if you can just download it right from DigiKey. The fourth choice, and probably the hardest, or definitely the hardest and most work, is going to be make the component your symbol and or footprint yourself based on the data sheet. This is something that comes up a lot when you're using more kind of specialized connectors that are going to be, there's only so many, even though there's a lot of them, there's only so many different IC footprints, integrated circuit footprints, that are out there. Transistors, different specialized ICs, even if they're very specialized, they're probably going to use somewhat of a common footprint. There's maybe 30 or 40 different footprints out there that most diodes, transistors, microprocessors, specialized chips, they all use relatively the same footprints, and they're widely available. Connectors are not like that. Connectors, there's for a million different connectors, you're going to have a million different footprints, and those are most likely not going to be available for some more esoteric ones. If you choose to maybe take a more out of the way connector, you're going to probably have to make that yourself. I'm not going to cover that tonight, but it's definitely something to keep in mind that you can do. As again, footprints, get them right. They are what the component sits on in the PCB. They outline the component, have pads or through holes for the pins, and they're going to contain a marking. So this little dot right here in the corner. If you get a footprint wrong and do the PCB and order the board, it's disastrous, right? You're going to have to, essentially, from that little mistake, you didn't double check your footprint, you're going to have to reorder the whole PCB, redo your design, and because it's very hard, if not impossible, to change where the traces go in the PCB once you've ordered it. And that means a lot of extra cost at the end of the day. So we don't want to do that. So it's very important, get your footprints right, double check them, double check, even if you've used one from manufacturer part search, which I'll show in a second here, double check, make sure you do it the right way, make sure the pins and the pads are what they should be based on the data sheet. So I've kind of gone through most of this already, but generally, first thing we do is the schematic. The nets are a node of single potential on a PCB. So it's like a node or just one wire is a net. And I'll use that term a lot tonight. And a port, so a net is just the label. A net names the wire in the schematic, and it also names the trace in the PCB editor. And you'll see that if you don't have nets, it becomes really confusing. And if you do have nets, it's really simple and nice to lay out your PCB. Ports are used to bring signals between sheets. Because we only have one sheet tonight, we're not going to be using any ports, but it's essentially if this output port signal was originating from this sheet, it's going to have an arrow pointing out or away. Input port, it's going to be coming into the sheet from a different sheet, and a bidirectional port can go either way. That's used for data signals such as I2C signal would be a bidirectional port, or a CAN signal would be a bidirectional port. This is a resistor here. You can see there's an R1. It has the schematic designator, and it's got the size, 1 kilo ohm. This res1 is an additional comment that Altium gives you automatically, and you can change that after the fact. And you want to try your best to make a clean circuit schematic. That is very, very important. It's very important so people can read your design later on and they can see what you've done. And it's also really important so that you can change your design later, change the schematic. If you have nets going and wires going all over the page, it makes it really hard to see what's going on. And I'm sure if anybody's ever done anything in multi-sim, you'll know what I'm talking about. If your TA comes along and tries to help you debug your simulation and you have nets and wires going all over the place, they're not going to be very happy, and they're going to want to see you clean that up. So that's important. Two other quick comments. Power ports are, again, very similar to something we'd see in Multisim or LTSpice. They are the ports, or the kind of the net names of your power pins. Ground is pretty self-explanatory. VCC, your supply voltage, and that it's a kind of a shortcut in Altium, as you'll see in a second here, that you don't have to type anything. You can just go up, click a button, and drop in that power port. And you can rename VCC or make any number of different power ports, 3 volts, 5 volts, 12 volts, whatever you want in your design. Buses are a little more advanced. We're not going to be using any of them tonight, but if, for example, you have a collection of digital signals, this is a great use for buses. For example, here I have part 2/3 of a 24-bit RGB data line and parallel data stream, and we have all 8 bits of each color going into one of these buses. So instead of drawing, for in this application, 24 different lines for the 24 parallel bits, we can just fold them into, I could actually have done this into one bus, but I just chose to do it into each color into its own bus. And I think this was somewhat necessary for just how Altium does bus ports between sheets, but it's just an easier way of collecting all of your signals into one line and drawing them between connectors and or components. If I had another component on this left side here, and I wanted to just bring this bus from, let's say, one component here, another one here, I could very easily bring this bus down here and split it up again into these lines to the other components, and very easily reassign which net went to which pin on each one, without just moving around the net names instead of redrawing the wires. But again, we're not confusing that. It's a little bit more advanced, but something to keep in mind for more digital type designs can be, and well, all designs can be used, but you can use these, but digital designs for sure make great use of buses. So all this PowerPoint will be sent out, but these are some schematic shortcuts that we'll use as we start to get our schematic design underway here, but we'll go back to Altium. And the first thing that we'll do, I've already got it opened up on the bottom here, is but open the generic components. So place is essentially where you can grab all of your different items for when you're doing your schematic design. This is also accessed through, it can be accessed through this taskbar at the top here. All the same components are available, and as well on this little taskbar right here. But for placing the components and getting that menu set up, we're going to want to go place, part, and then that brings up your components. And then there's a couple different ones here. There's simulation generic components. That's for simulation. Not going to be using that right now. Miscellaneous devices and miscellaneous connectors. Miscellaneous devices is what you're probably going to be using the most. It's essentially Altium's library of all the very generic basic devices. It's got tubes, even though you're probably not going to be using any of those. A bunch of different transistors, switches, resistors, PNP, NPN, MOSFETs, op amps, LEDs, everything that is on the more generic side. Lots of different diodes, capacitors, etc. So for our circuit schematic tonight, I'll start with the resistors and the diodes, and then we'll move on to the two chips. And there's a little power connector that's going to come in there as well. So starting with the resistors, there's I think three different footprints that it gives you. So for both the components and the manufacturer part search, Altium gives you both the schematic preview and the component footprint preview, and this is in the 3D view. So you can see here, this is just your regular, quarter watt axial resistor, and that's what we'll use tonight. So to place it, we can double click, and it gives you a 1K resistor for the default. So we're just going to place, we have 1, 2, 3, 4, 5, 6, 7. So we have 7 resistors, and you just click and it automatically regenerates them as you go. I'm going to put them kind of roughly where I need them at the end of the day. Here, I'm going to put 7 resistors in. Next, we need one larger 47 microfarad capacitor. That is going to be a polarized capacitor with a 2-hole one here. There we go. Yeah, a larger, slightly larger one. That's probably going to be what we're using. So we need one here. When you're routing, so in the schematic editor, spacebar, flips around the component, and when you scroll up and down with your mouse cursor wheel, then the schematic scrolls up and down. If you shift and scroll, it goes left and right, although what we'll be doing right now while I'm placing the component. Left and right, there we go. Left and right, scroll, and then control scroll is zoom. And that is true for both the schematic and the PCB. So there's our one capacitor there. You'll notice that when I place them, they don't have their designators. They're just a question mark. So that will come later. Rest assured, I'll explain that, but that's something that we'll cover in a bit, and that Altium annotates everything at the same time. It works out quite nicely. So there's 2 more capacitors that we're going to need, and these are just smaller surface mount semiconductor capacitors. In the about 10 nanofarad range. So we can use, and tonight I'll show you kind of a mix of through-hole and surface mount design on the PCB. So we're going to come here, take our cap semi or semiconductor capacitor. There's about one right there, and one right here. Last things we need are, in terms of the basic components, are the diodes, both for the LEDs and the blocking diodes. So in this schematic, they specified a 1N4148. We actually have one of those here. I don't know why Altium has such a crazy assortment of diodes available, but they do. So I'm going to use 4 of these. And then we need 3 LEDs. And this is your typical kind of round plastic LED that you probably used in 1450 or in, any number of, it comes in all the hobbyist kits and that sort of thing. We'll use, there's another one, same footprint, another one. Now this is a surface mount footprint, maybe, I don't know what size that is, didn't say. And another surface mount footprint. This is slightly different, but we'll stick with this normal through-hole one for tonight. Double click on that and place 3 of those. And all of these have various, you can change their component values. So for these, properties window in here. With these ones here, we don't hit the designator yet. You could, but it's just easier to leave it. And I will change, you can either change the comment, you can set that to the value. Are those IR LEDs? So we have a question in the chat here from Ryan. Are those IR LEDs? I think they are. Okay, so you're right. It does say components here. In components, typical infrared LED. That is for, I believe, the simulation. It looks like this text right here is for a SPICE simulation. For our purposes, we just care about, so we're not, again, if you're doing a SPICE simulation, by all means, you'd want to use the right one, because an infrared LED is going to have a different forward voltage drop and average current than a red or green or blue or white LED, and you're going to want to get that right. But I think for this case, it's just a basic, one of those axial, no, not axial, but the 2-lead LED in the plastic case. But you are right. These will have, I believe this is a gallium arsenide infrared LED with a different SPICE file than the other ones. Which means I guess you can use these for simulation components as well. I did not know that. Lucas has a question here. Can we change footprints after making the schematic? Absolutely you can. I will demonstrate that for sure. That is definitely something you can do. The schematic symbol is not locked to the footprint. It's that you can go back and forth and change it after, and that happens all the time. You might forget to do that, start laying out your board, and then go, oh no, I have to change it, and then go back and change it, or select a whole different a component overall. So once again, we'll go back to the resistor here, and we'll actually just change it right now. I'm gonna just to make this whole thing a little bit nicer, I'm just gonna hide the 1K resistance value. This little I here is just, you can either view it or you can hide it, and I'm gonna change this comment here. This one is a 22K, and also just to make it easier, I'm just gonna delete that and copy paste that one down there. This one here is a 10K. The top, this capacitor here is a 0.1 microfarad. 0.01 microfarad, actually. This one down here is 6.8 microfarad. So 6.8. My apologies again. 6.8 nanofarads on the side. On that. This resistor is a 100 kilo ohm. Once again, these values that you assign to the resistors, they have no bearing on how you lay out your board. It's just so you know what size it is for when you actually go to both order your components and go to make the board, and you're referring to your schematics. It's for you and for whoever else is reading it in the future to keep that in mind. So we don't have to worry about that right now. I shouldn't say that. We may have to make sure your component values are correct, but this is not something that actually influences your physical realization of your design on the PCB. So, of course, we also need, do they print, okay, so Navjot is asking here, do they print these values on the PCB? You can, so that is based on the footprint. Generally, no. What gets printed on the PCB is the designator R39, C27, whatever. Then you have to go and back to your schematic and reference your schematic. Control F the PDF to find whichever component you're looking for, and then double check to find what size value. You could print it, but it would take up so much room, I would say, that I think it's generally that's not a typical design practice. But good question. So we're going to go now to miscellaneous connectors, and we just need a 2-pin power connector. And I actually did a little bit of searching in here earlier today. There is a 2-pin header that we can use, but to make it a little more realistic, I actually want to go now to the manufacturer part search, and we'll find the 3 other components. So I actually already have this loaded up here. I just searched power jack, and I found a power jack that fits our needs here. So this is manufacturer part search, and it's found by going to View, Panels, and then manufacturer part search. And I just turned it off, so let me go turn it back on. Okay, this search line at the top here can be used to either search just like power jack. You could do 60 ohm, 560 ohm resistor, or any 555, like I'll do in a second here. And then it pops up with a bunch of results. If there's a little kind of circuit symbol here, firstly, if it's green, that means it's in stock somewhere at some distributor or supplier somewhere, and you can actually change which ones pop up here in your settings in Altium. The little green symbol here means that Altium has a component footprint available for it. So select. You can see there's a bunch of different ones here. Power jack is a pretty common term, so it's going to probably pop up with a whole bunch of different results. This one here from Switchcraft looks pretty good for us. So to place it, we're going to go at here. There's a download button, but in the drop-down menu, there's place in the corner, and then it pops up with our component. But I don't like those pins going out to the left, so I want to flip it around. To flip something, mirror image it, you want to hit X, the X key to mirror image it, and then click and place it. We don't need another one, so we're going to X out of that, escape, and that looks good. There's our power port. And before we go any further, I'm just going to set that up as a power port here. Pin 3 here is the center pin of the power jack, so we're going to give this a VCC net. Up in the top here is my VCC power port pin, and we're going to click that. It generates a VCC, and I can keep adding it to various ports. Maybe I want a VCC up here eventually. Add another one there. And once any resistor or once 2 elements in Altium or in the schematic editor are joined together, you can actually drag it around, and it'll automatically generate wires to keep those components joined. So I can drag my VCC out like that, and it makes it maybe look a little bit better, brings it a little farther away. You'll also see here these little red error bars, kind of look like when you misspelled something in Word. That is means that there's an error, and most likely in this case, it is because all these components have the same designator, like R question mark, and it's because the we haven't assigned them a designator yet. These two pins on the bottom here, pins 2 and 1 on the jack, are both should be set to ground. So we're going to ground that, and then we're also going to introduce now wires and drawing wires. So wires are drawn by using the two little squiggly blue lines here in parallel at the top, and we're just going to connect those 2 points, and then that's connected. That's set up. So now that's our power jack. Now the only 2 things that we need left are our 2 ICs. So again, we're going to go in the corner here, and we need an NE555DR. Search that. And there's a bunch of different ones that pop up there. This one here is actually, I don't believe it's in stock, and it's only in stock at Newark. So this one down here, this NE555DRG4, doesn't have a footprint. So it looks like only there's one of them with a footprint. So we're kind of stuck with that one, but keep in mind that pretty much all NE555 timers are going to be the same. These are all surface mount, as you can see, between them. So, you know, we're not going to have a bunch of problems if we have to buy this, if we have to use the footprint from this one and then buy this other one here, but you should still double check on the data sheet. So again, to place this, we're going to go download, place, and it pops up with a timer. And I already know that C3 has to go into the, sorry, not C3. It's C3 in this other schematic here, but I'll change that around. So we're going to get that out of that. Another nice thing about manufactured parts, which is we can automatically assign all the component parameters in the schematic. It's very important to, especially for your chips and other maybe more important circuit components, and you should do this for all of them, but especially for the larger ones, to assign the supplier links to a part. So even though we place this part at the top, we can still assign add the supplier link and the parameters from a different part. This one down here, let's say we want to actually buy this one here from DigiKey. We like buying from DigiKey. We want to add this NE555DRG4 parameters to our part. So we can just click, so right click on here, click there, and then we're just going to select our part, and it pops up with the DigiKey part number, and then we can just escape out of that menu. So now we have the DigiKey part number on our part here. Again, we're going to do this similar thing for our counter CD4017BE. 2 of them have component footprints, and we'll choose this one. This CD417BE is the one we're going to use from Moser. So again, we'll place this one. Looks pretty good. Come here. We only need one of them. And again, we'll assign the file link and parameters. Part and Moser part number pops up. So now it's just as simple as essentially, you know, drawing the wires between all our components. So I'm just going to quickly do that. You can, Altium keeps you in wire drawing mode. You know, if you keep just keep kind of routing here, it'll keep giving you the option to route. So we know that the diodes, the grounds of the diodes, all are going to be connected together. And when I'm open-ended here and I don't have anything else, you're going to right-click, and that ends your wire kind of just open to the world. There's nothing connected to it. Eventually, we'll put a ground pin on there, but we won't do that right away. There's these four dials we're going to have to bring, because these are bigger than the spacing of these pins here. We're going to, you know what, we actually need 3. But now the other one is not needed. So we're going to have these 3 here. 9, 8, 7, and 6 are going to go into these bottom 4 here. I apologize for my fan. I know it's going pretty hard here, but hopefully it'll slow down in a second. There's various ways you can, you don't have to do this right angle way of drawing out the schematics. I believe it's shift spacebar gives you different trace options. So you can do, this is, and the same command is true for in the PCB editor as well. You can do right angle traces or kind of however you want. I think there's a circular option as well. So I'll go for that. We'll put those together. You also see that just in the as we're editing here, some of these designators get covered up, and you can always move these around after the fact. So our VSS is our ground pin, so we're going to put a ground pin there. I'll put another one here, as I said. VDD is our VCC. These two are equal, so we're going to put a VCC port there. And we want our reset node high. Connect this. Sorry, I can connect. We want to hold our reset node low, so that's why we're going to actually connect this 100 kilo ohm to ground. And we also connect the clock inhibit to ground as well. Over on the 555 side here, we have this capacitor here, and 5. Ground, VCC, reset is held high on this one because it's a reset, active low reset, where you can see with the bar across it, the top. And then we have our timer bridge of 3 components here. This gets VCC on the top of it. And this node in the middle here is discharge node. So we're going to put a net name on it. So net names are accessed by this little button at the top here that says net. You can plop a net name there, and we're going to rename it. Put this in here. Discharge. Now, this name here doesn't have to match this name here. I will, draw a wire and then copy this net name over. But it doesn't have to match. You can spell out the name discharge or do whatever you want. It doesn't have to be the same as this on the schematic itself. So now this discharge node right here and this one on pin 7 are connected. Trigger and threshold have to be connected, so we'll do a similar setup right there. Trigger is actually going to come down here and tie into right there. And we'll put another name and copy that over here. Okay, and that's it. That's done. We probably want to add some net names in to help us while we're routing. VCC and ground automatically come up with their net names, but let's put one there, one here, one there, and then that'll be it for now. That'll kind of give us that. That'll demonstrate that having net names is a good thing, and not having net names can be just cause some headache when you're doing your routing. Right, so that's good. That's all done. Now you'll notice that on the counter here, there are some pins that we didn't use, and just to make sure that Altium knows that we're not going to use those pins, we want to put a little red X on them to make sure to tell Altium that those are unused pins. So we're through those X's. And that just lets, like I said, Altium know that we're not planning on using those pins. They're dead. They're not going to be accessed for our schematic purposes. So that's that. I'm going to go back to the PowerPoint now for a second. That just something to keep in mind as you do your schematics here is that Altium has design rules that are mainly have to do with the PCB, but are essentially a set of constraints that will guide how you design your PCB. But you should always keep these in mind as you're doing your schematic design, because at the end of the day, how your PCB gets made is really dependent on what the capabilities of the manufacturer that you're going with. So if you're doing, PCB way, for example, is an example of a manufacturer. Every manufacturer should list the capabilities that they have in their design shop, in their fab shop. That, how big of a hole can you have? How small of a hole can you have? How small of a trace size can you have? How big of a trace size can you have? What's the biggest board you can order? How many layers can you do? What's the thickest copper? As just a few examples of this picture here is of differential pairs. Some rules that Altium gives you. So, for example, the preferred width, the preferred gap, the max width, the maximum gap between differential pairs, and the width of the trace as well. So, with this kept in mind, you still want to keep as close, with a good margin of safety within those tolerances that the manufacturer sets out for you. Because if you're right on the ragged edge, you're probably going to get burned, and you might find that, even though you were technically within the limits, there's still something that didn't quite work out when you got the board ordered. So there's just a few things to keep in mind, kind of best design practices as you go along here. So I'll come back to this in a second once we have moved the PCB, moved this circuit onto the PCB. So the last thing essentially that we're going to do here in this, hopefully will take away all these errors, is we're going to annotate our schematics. So if you go up to Tools, Annotation, Annotate Schematics, and that brings up the annotation dialog. And there's a bunch of different options here. I'm not going to really talk about many of them, except that there's an order of processing that Altium gives you. You can either do across then down, up then across, down then across, or across then up. Across then down is usually what people use. That just makes the most sense. Kind of that's how we read a book, and that's how you read schematics. You can either do across then down or down then across. Either of those would make sense. Any of this one, like across then up, that's just weird. I would not do that. So for now, we're going to do across then down. And what we want to do is, it's not just this kind of a switch, a quick go. We want to go update changes list, and then Altium kind of thinks of it, makes the changes. Okay, now these are our new ones that are listed here. And then we see those, we go, okay, that looks good. Then accept changes and create eco. And eco is an engineering change order. And this is something that also comes up when we move into the PCB. And it has all our new component names here. And you can go validate and then execute. Close and close. Now we can see we have no more red bars, and everything has a schematic annotation on it. And now our schematic looks pretty good, and that's pretty much done. Except for, I forgot to put a ground pin on this capacitor here. Okay, now it's done. Now we move to the PCB document. So to do that, we have to add in the PCB document to our project. And you go into this here, add new to project, PCB. Takes a second. Now this is your PCB document. And pops up here, and we'll save all active documents. So as with anything else, save often and save regularly when you're doing your PCB design. I didn't even save the schematic document. So of course you can change the name of your document. And okay, so now we've got our PCB. This black board here, default, it's 4 by 6 inches, and this is the actual printed circuit board that Altium is going to give you. And now we're going to move our components into the printed circuit board. So this is our schematic here, and to move it into the printed circuit board, we want to go up to Design and Update PCB Document, and we've called it PCB1. You can call it whatever you want, and that's how we bring all this stuff into the PCB document. So this is once again an ECO for all our components. This is the list of components we're adding, the list of nets that we're adding, and the component classes and rooms. Rooms, as you'll see in a second, cause a bit of problem. Normally I would uncheck this, but I'll show you that you should uncheck it, and I'll just give a demonstration here. But normally, deselect the rooms. Rooms are kind of a weird a function of Altium that is maybe helpful for some, but has been found by myself and everybody else that I've talked to be a little bit of a nuisance. So you hit that, you can hit validate and execute, or just execute them, and close this. Now we have all of the components on the slide here. So this room is this kind of red box around it. What it essentially is if you move one of these components outside of the room, it gives an error. An error in the PCB document is when a component turns green. So if I move the counter out here, you can see all the pads are green. That means there's an error, there's something wrong with it, and because it's outside of this room. So I'm just going to delete the room, and then we're not going to have to worry about that. That's just kind of a side thing that we have to for just general reference. But we'll go back to the PowerPoint here for a second. I'll quickly go over some definitions. So the picture I have here is a 2-layer board, and the traces, as I mentioned, that are on top of the board, those are the actual metal or copper wiring that's been printed on the board, and that's what we're going to be laying out here in a second. Vias are the holes plated with copper on the inside. You can see 2 of them here that allow the signals or electrons or whatever you want to call it to go between the layers, and we'll for sure be placing a few of those as we go here. Planes or polygon pores, and there's a larger section on this part in this PowerPoint later, are solid layers of copper that are usually used for ground or power distribution. We'll put a ground plane on the bottom of our board in a little bit. Solder mask is kind of the green. Yeah, I'm sure all of you've seen a standard green PCB before. That is the mask that goes on top of the solder. So if you drop like a coin or some metal touches between 2 components on your printed circuit board, it doesn't automatically short everything out. And solder masks can come in some different colors, and it gets printed over the whole board except the pads and the vias. The silk screen is what you might see as like the white writing on top of the PCB, and that's the topmost layer. So as we just saw, this is what we get. The black rectangle is our PCB, and we get all our component footprints in the corner here. That component, all these little lines in the component footprints here are called the rat's nest, and that's what Altium gives you to where it indicates where the traces need to go. That's not the traces themselves, they're not already there, but that's where they need to go. And what your job is, as the person who's laying out the PCB, is to lay out the traces so that all those rat's nest disappear. Like I said, component placement is crucial to the board. If your components are placed poorly, it actually becomes pretty much impossible to route the board. So, and I'll definitely spend a bit of time on explaining that here. The rat's nest is going to guide your component placement relative to one another and to all the other components. And in general, if your board allows it, you could even lay out your components in a similar manner to how your schematic is. Unfortunately, though, the schematic symbols that you get are not the same as the actual component footprints, and moreover, you can't just use a net and a net label to bridge your, for example here, discharge and bring it over here and have just kind of an imaginary wireless transmission between these two. That, of course, does not work in the real world. So we need to physically connect those nets, and we'll hopefully do a little bit of that. I'll show you how to do that here. So here's an example, bad placement. All these nets, a bunch of them are crossed. It's going to become really hard to route this, if not even impossible. Like, it's almost, I don't have to really explain this very much. It's pretty obvious that everything's crossed here, and it's going to be really hard. Here, you see these nets are straight through. These three probably share the same pin here, and you want to, as much as you can, make your rat's nest look like this before you start routing, so that you don't have to kind of revisit your component placement over and over and over again and change things around and delete and reroute and all that kind of stuff. So make it as nice as you can before you start routing, and that's going to give you the best results. So trace sizing, also very important. It's similar to what you would have in wiring sizing in your house. You have different size wires for different current loads, obviously on a smaller scale here in the PCB, but generally 15 to 20 mil. Mil is 1/1000th of an inch, if you're not aware, and trace sizes are usually given in like 8 is really small, or 5 is a really, really small trace, but like generally you start your traces at 10 mil, 15, or 12, 15, 20, 25, 50, 100 kind of situation. So 15 to 25 mils is pretty good size for your traces. Sometimes larger if you need it for the power handling, but you can use an online calculator to find trace widths. And there's a few different, when you're using those calculators, it'll ask you for the ounces of copper that's ounces per square foot of copper. That's just a general unit that's given. Usually it's either 1 ounce or 2 ounce. A 1 ounce board is the average size board. A 2 ounce board is used, and you can get even larger boards than that, thicker copper layers than that. But 2 ounces is what's most normally used for power boards, and boards that are the main thing that they're doing, is distributing power. And I'll get back to grounding in a second here. So now we're going to start laying out our board. Some things to keep in mind is, for example, this J1 here, that's our power port input. Obviously, this can't go in the middle of the board. It's the power pin, and we want to put this on the end of on the edge of the board somewhere to aid in our, so just to plug it in. And I'm going to pick kind of a little bit randomly, but let's just put this corner, put this over here. So you can see that the rat's nest, moves as you move around the component. It updates automatically. Another design tip here is to regularly go between the 2D mode. So right now we're in the 2-dimensional mode and the 3D mode. Now this is accessed by hitting either the 2 or the 3 keys on the top, the actual number keys, 1, 2, or 3. The number 1 mode is the board size definition mode, and that allows you to change the board size. And I'll do that maybe a little bit later, but this is just to show you, this is the board definition mode. 2 is the mode we're in, and 3 gives you your nice 3D mode. Now, a benefit of taking things from manufacturer part search is, in a lot of cases, the Altium built-in libraries do not have 3D bodies attached to them, but manufacturer part search does. And you can see here that we have our little black boxes and gray boxes for the different components. That any 555 actually have Texas Instruments written on it, and it's actually pretty accurate. Some of them are, obviously this capacitor is just emboxed, but this IC here is actually pretty accurate to what it would look like in the real world. You can move around in 3D mode by, if you hold down Shift, left click, that allows you to actually turn stuff around and get a visual, and you can, again, scroll, control scroll, and shift scroll for the different up, down, in and out situation viewpoints. So go back to 2. You can only see it flat on in the 2D mode. So here we have the timer and the counter as kind of the central integrated circuits that we have on the board here. So actually, it'll probably be the easiest if we lay out at least the counter, similar to what we had on in the schematic. So we have here, you can see here, this is a net that I named carry. There's ground, clock, but now we have this net called net C2_1. Well, what is that? Now we have to go back to our schematic to see what that is. Okay, C2_1. This net is actually the reset net. So let's say I've decided, okay, shoot, I forgot to name that. I want to go name this net now. So I'm going to put in another net label. Right there. I'm going to reset. And now I want to re-update the board. Design, update. There's only this one. I can even add that. What the heck? Interesting. Oh, maybe it didn't save it. I thought that should do it. Ah, interesting. Did not work that. Oh, I don't know why that's happening. Usually, it allows you to update your design and your nets while you're running. But similar to the schematic editor, to flip the component around while you're running, it's spacebar. And again, you can drag it any way you want. So I'm just going to line these diodes up, kind of in similar to how we had them in the schematic. Having these outlines kind of simplify and allows you to see where components are going to be as you're soldering. This is obviously what the LED actually looks like in the real world. This capacitor is pretty big, probably doesn't actually need to be that big, but well, again, it comes down to what part you've chosen. And again, you can click and drag groups of components as well. You can pretty easily see up top here that we have a much larger PCB than we're actually going to end up needing, and our nets are all crossed and everything. So this timer here is let's see here. Trigger and discharge are on the same side, and I know from what I laid out before that we probably want to put our R3 and our R5 on that side, the same with C3, so we can go to trigger and run discharge all on the same side, and the same with BCC is on this side as well. So actually, yeah, I'll do that. Okay. So I think what I said R3, yeah, right there, and R5. There we go. And we know that we also need C3 up here in the corner. So now we've picked that we want these components to be right here. Now we can start routing. So to route trace on the board, you're going to go to this little triangle shaped symbol, interactively route connections. And Altium will give you a kind of a default size. So to change the trace width as you're routing, you're going to go Shift W. That opens up this choose width dialog, and you can change it. I'm going to pick 20 mil for what we're doing here. Keep going. These through-hole pins, you can access both sides of the board. To change the side of the board, you can go down to the bottom here that you're routing on. There's a bunch of different mechanical layers, but the two layers that we can actually route copper traces on are the top and the bottom, because it's a two-layer board. For the bottom layer, and we can route, trace on the bottom, and it becomes blue. But I'll try to get everything on the top for this, because that will allow us to do some power ground thing on the bottom. And for nets that we know that we're going to have a plane for, such as ground, or we want to have a plane for, I'm not going to route that, because that is going to be this because the through-hole pin is going to be automatically connected to the bottom ground plane when I actually go and route that at the end of the day. So this BCC pin here, we know we have to connect it to this VCC pin here. This ground is crossed, but once again, this is going to be through the board, and we don't have to worry about that because the whole bottom of the board is going to be a ground pin. And I'm going to move this a bit closer. And while I'm doing this, I will actually show you guys. Design in the board edit mode gives you edit board shape, and you can take these little grab handles here and just change the board shape, and then it just, it modifies the board to whatever size you want. Let me go back to the routing mode in mode 2. And I realize I'm on the bottom. So to change layers while you're routing, you want to hold down Control, Shift, and Scroll. And what you can actually see that what this has done here is it's automatically given us a via to get on the other side. But because we want to route on the whole thing on the top, I'm actually just going to stay on the top and go into here. But now I've realized that this is the VCC, which is the power net. So this circuit right here, this R3 R5 C3 combo, is not going to draw much power. But maybe I'm thinking that, I don't know, maybe this this isn't a poor example, but maybe this 555 timer is actually going to draw some power. So maybe I want to set a bigger trace. I'm going to trace up there, but let's say I want to make it 25. Now, actually, I realized here that this trace size is a 10 mil trace, and why that is that this actually didn't get changed. Why that is it has been forced to be that way through the design rules. For some reason, Altium forces you to use, at the beginning, it gives you a 10 mil design rule size, or for the width of your routing. So it says here min width 10, preferred width 10, max width 10. So just to give us a wide value of what we can use, we go 100 mil with max, preferred is 20, and min we'll keep at 10. And apply. And so now, if we wanted to, we could use now we should be able to use 25, for example. Yeah, so now we got our BB trace to get that ground, or the VCC to U1. Yeah. We also know that we need to bring trigger to here, discharge to this pin right here, and we can bring trigger actually right under the UC, not the control, but the 555 timer here, to the trigger pin on the other side. We also know that we're going to be routing ground on the bottom, but we're going to need some way to get the ground signal to the top. And the easiest way to do that is to just drop in a via right beside it. So again, I'll probably want a bit of a larger trace for ground. And like I said before, Control, Shift, Scroll gets you your via, and just place that, and then I'm just going to X out of drawing anything on the bottom because there's going to be a ground line on the bottom. Somewhere here, once again, this capacitor doesn't need any ground on the bottom there. We can run, so now there'll be a bit of a problem. We need to get our output signal over to the timer, to the counter, but we also need to get our VCC up to the top pin here. For that, we're going to actually go underneath, underground, on the bottom layer. We can drop a via in on the VCC pin. It's giving me an error right now, but as soon as I drop it, it automatically changes the net of that via to ground. To VCC or whatever net you dropped it in. And I can now select num on the bottom. So here, and I just run my VCC trace underneath, and once again put a via in there, and I'm back on the top, and now I've got my VCC back on the other side, back on the red, the top side for the red, and back to give this VCC to the other pin there. So now, this is a bit of a larger chip here, this through-hole chip here, and we probably want to line up and get the output net on the same side. So we also know that the output net goes through one of our resistors here, R1. I'm going to put this resistor in the middle, and our clock pin is on the other side, so I'm going to flip this around. And I think that will work pretty well, actually. And I'll just keep going with the 20 to 25 mil trace that I used here. Generally, larger trace width sizes are better. They have lower impedance, and yeah, that's the main rule. The main thing is lower impedance for your trace sizes. If you can use larger trace sizes, then definitely do that. Sometimes you can't because you have a lot of pins in a small area, and that's what you're limited by. Now we can route our VCC down to the VCC pin here in the corner. And we have our C2, which is going to be held up to VCC. And the nice thing about, so surface mount components, you can actually put them right in the middle of a trace, and it will automatically get connected to the trace. You can kind of just run it through the pad. That's for some applications. High power applications, I wouldn't necessarily do that because you could have a bunch of heat going into a component, but this counter is going to be drawing a pretty low pretty small amount of current, I would imagine. So it's going to be, even though it's driving those LEDs, it's not going to be pulling maybe more than 70 milliamps or maybe 100 milliamps, I would guess. So that's acceptable in this case for a 25 mil trace. I'm going to connect those two nets there. Okay, let's see here. So this is where having named nets is definitely helpful. So I can see, okay, R7, I now need to connect this to D6. D6 needs to go to ground. So, okay, so let's say I actually now have decided I will put all these diodes at the top here. It might be the easiest thing to do. Because our output here for R7 is going to be one of our LEDs, and I think that's the carry out. But that might actually be the yellow. I think that's the yellow one. That didn't really matter. D5. Let's put that right here. We have D2. So this net here is this D2 underscore 2 is going to be a common net, I believe. I'll put those three really close together. We can route our signals. And you can see here that I'm still getting a lot of ground nets that are, crisscrossing. And had we been using a board, had we been using the bottom layer for signals, and I had a bunch of other signals on the bottom here, then that would be a problem. But because we're using a board and we're going to be putting this ground plane on the bottom, and the only signal I have on the bottom right now is this VCC extension, and then ground will go all around that. It's going to be, you'll see it, once I put that plane down, it takes everything away and it goes, it becomes really nice. So I'll put our 6 right here. And then we have our D3 diode. So you can see that I'm kind of laying the components out as I go. But what I do personally a lot of the time is picking the components that have the largest number of pins or pads ahead of time and designing your layout around those components is generally the best way to go, in my opinion, because you'll find that those components with a high number of pins end up driving how you lay out your design, because that's what everything connects to. So that's just a little my opinion there for how you might doing a different board with other ICs. Design, try to rotate the ICs and arrange your components so you have the fewer rat's nest wires kind of crossed over. That's the best thing to do. So this C1 here has to go to ground on the timer. So we'll route from here to the one pin of C1, and then you'll notice that I could do a via to ground here, but all through holes for as far as the ground net is concerned are essentially vias. So we're gonna just pick one of those, and that'll be routed to ground when we put the bottom plane on. R4 and R2, I'll call the other R4 here goes from C2 to ground, and actually what we can do is just to make things really fit in here a little bit closer. We're going to actually put this one right here, and you can move the designators of these components around when they're not locked. So I'm going to put this R4 down here, and then this actually becomes super, super easy. Just boom, put that together, and that's kind of all close in there. And the last thing we have to do here is just this last diode, and I'll put the resistor down here, and diode, it doesn't matter, right there. So I guess maybe not the best example if we wanted all three diodes facing the same way, but they're all still there, and they're all still going to turn on. One other thing I would say is for most physical boards that you want to make, you're going to want to put some sort of mounting holes. So we're actually going to put you can either use vias for mounting holes, or you can use through hole bodies for mounting holes, and you can. One way to do that is to go into place here, place pad, and we actually get what is essentially the same as one of these through holes, and we can click that, and we're going to, so this is the pad, change size, and we can go here and we can change the net of the pad, and we're going to set this net to ground. Usually your through holes are set to ground. So it's one way to give a ground to your ground signal to your board, or to kind of bring it to equipotential with everything else. We're going to change the hole size itself to, let's say, 150 mils for a larger screw. Now you can see that everything went away here. But we're going to change the annular ring, or the size of the exposed pad around the hole to, let's say, 200 mils. And there we go. That's good. There's our ground hole, and I will copy and paste that kind of roughly into the four corners of our board. And I'll actually just put one. We'll just put one right there for now. We'll put another one there. So now what we're going to do, then I would have to assign those holes individually to ground. So I'll go over. Okay, before I do the pour, the last thing before the pour is we see that the size of our board here is pretty large compared to what we have on it. So we're going to want to change that. So we go back into the board definition mode, number 1, design, and modify board shape. Run this time, because now we actually just want to cut off part of the board here, and we can do this to a nice angle. make a board look kind of cool. There's angle slide on it. Okay, there we go. Back to the 2D mode. And now we want to put our ground plane on. I'll set these other two through holes here to ground. And now we want to put it on our plane. So to do that, we're going to go place, polygon pour, and we're just going to give us this this crosshair here. And all we really want to do is we just want to trace out our board and leave a little bit of a room on the outside. Across the top here, down. And actually, I realized here I'm starting to route this polygon pour on the top, and I don't want to do that. So I'm going to go down to the, make sure to switch down to the bottom layer here. And NavDot's noted that we use 4-layer boards to give ourselves more room to route traces, and that's 100% true. That things get really complicated if you're just using 2 layers, and it becomes really nice, simple, and easy to do that when we're doing if we use a 4-layer board, and that's completely right. Just going to lay out trace like that, and then I'll have to go back up to the top here. And right click when you're done, and right click again to go out of it, and now there we go. Now we're on the bottom layer, and that's our polygon pour. Now we have to set the polygon pour to ground. Double click on the pour, and the properties dialog opens, and we want to set the net to ground. Okay, and now we want to go. We have to re-pour the polygon pour. Tools, polygon pours, and re-pour all. Now you can see that every net that is connected to the ground has these little connections to it. And you can actually specify how Altium connects to their nets. You can either go all the way around, it can just be the net, the one ground via here, or through hole can be just one with the bottom pour, or you can have different connection setups. Whatever you want, and that's specified in the design rules. So there you go. That is essentially the finished board, and we can see it in 3D here. Nice view of it. It would be cool if we had the LEDs, but we don't. And you can actually see here on the bottom. If I fling this around, this different green here, you can actually see that the polygon board has been put in. I personally like to use. I'll just go back to 2D mode here. I personally like to use the types of interconnect from the polygon pour to your through holes and your vias, that it goes kind of solid copper all the way around, because that gives the best, especially for ground, that's going to give you the best low impedance connection and just the best connection overall. So Lucas is asking, is there any reason why you wouldn't put a copper port on both layers? And that's a great question. We could do just that. Generally, yes, you would put a pour on both layers, because that's going to allow you. You can think in a more complex board with more signals. Maybe you have to route even more signals on the bottom side, and that it may work out that there's actually one half of the pour kind of gets split from the other half, and you would put one way to get around that is I'll bring up a board here that I did a little more. It's a little more complicated with. Well, a fair bit more complicated with a microcontroller and a whole bunch of other peripheral devices on it. Here for the Formula Electric team, it was a control board for a motor controller, and you can see here that the pores, the plane has gotten split up, right? It's not, because I had to route signals on both sides, it's not one solid thing. It's all a bunch of different bits and pieces. And you're right, you're totally right, Lucas. The best practice for, and especially this case, is putting pores on both sides, and you're gonna do what's called via stitching, which is essentially all these little vias that get put in. you don't have to do that yourself. Altium does that automatically, and that essentially nets the two pores together, so it's kind of equipotential, and all those different areas of the pores that are kind of split from each other get connected, because most likely at least part of that, that polygon on the other side connects to the polygon, the ground polygon that's kind of close to it, and then it kind of just ends up connecting the whole board. At the end of the day, you might have some regions that, or some nets that actually don't, and those are called islands. You can either tell Altium to put copper there or not, and you might have to check if some of those nets are connected. So this is just an example of a more complicated board that you would do that via stitching and a polygon on both sides for. Of course, the ground plane can also help with draining EMI and types of interference. So the last thing we would do before, so at this point we'd save it. And maybe I'll go back to the PowerPoint here. You'll see here I've told you a bunch of this stuff. Grounding, best grounding is with the copper plane. Polygon pores, I've gone over that. PCB layout shortcuts. Again, you're going to get this PowerPoint, so you can go over everything. I realize we're almost at the end of time here, but the last thing we're going to do is put together our bill of materials, do a design rule check, and generate our fabrication files. So first thing is a bill of materials. And that can be done two ways. You can either add a new thing to project, active BOM, select that, takes a second to come up, and generates this active BOM document. First thing we're going to do is change our currency to Canadian. Now, most stuff in here is actually not filled out. It's not very helpful to us because we use the generic components. When you take something from manufacturer part search, it automatically adds in that, or it's very easy to add in that extra bit of information which specifies the supplier link for the component. And then you can very easily come up with what your overall cost for the board is going to be, and actually create your spreadsheet of list of stuff, components that you are going to upload to, not necessarily upload, but you're going to use when you're going to DigiKey or you're going to Mouser or whatever supplier you pick to actually order your components for the board. So we'll save that just in here, and we can close it. And we'll save our project at the same time. So last thing we want to do before we generate our files is run a design rule check. Access to Tools, Design Rule Check. And this checks our board against all the rules that Altium has set out. Now, you can change the design rules to kind of whatever you want. Like, you could set that you can, you can create short circuits and something, and Altium won't check for that. So you have to kind of use it with some intelligence. It doesn't know what circuit you're trying to do, right? At the end of the day, you are responsible for the circuit that you're trying to put on the board there, on your board. And if you mess up and you tell Altium that you messing up is okay, well then obviously Altium is not going to catch that for you. So you have to be smart about how you set up the design rules. And a lot of the time, your design rules are going to be based on those manufacturer tolerances that I mentioned earlier. You're going to go to the manufacturer page, whatever that's JLC, PCBWay, whatever you want, and they're going to list what their tolerances are, and then you're going to add, some percentage on top of that to be another margin of safety. Whatever would make sense, or what is a logical margin there, and then you can put that into your design rules, and then you're going to check them against your design rules. So design rule check creates a report file. It lets you know what you've done, and it stops. You can set it to stop when X number of violations are found. Sometimes you have a lot of violations that are, we'll see when this comes up here, but it might be something that is has to do with the solder mask. The solder mask sliver around a through hole or a pad, and those errors are not as important, not as critical, or errors between the silk that have to do with the clearance between the silk screen and the solder mask. Those are errors that come up a lot as well, and those are, again, not critical, but if you can fix them, then that's the best thing. So we'll click run design rule check, and we get our design rule verification for it. And we got 21 rule verifications. And those are split across silk to solder mask clearance, like I was talking about. And the other are hole size constraint. So let's actually see what hole size is. Okay, so we've set a maximum hole size of 100 mil in the design rules. Now, I know for a fact that many manufacturers can do a hole much bigger than 100 mil. 100 mil is only 1/10 of an inch, so it's pretty small. And I'm sure, it's would be very common for all manufacturers to do hole size larger than that. So the best thing to do in this case, I'm not going to do it today, but what you would do is then you would fix that and you would put in the actual value for your manufacturer so that it properly checks it. You wouldn't just kind of ignore it, because we have these three, we have, 7 violations. So we want to make sure that, if you had 100 violations, well, you're not going to go through and check each one. You want to change the hole size constraint and run another design rule check against that. The other issues here are silk to solder mask clearance. So that's pretty fast, but essentially it shows this silk outline is actually too close to the solder mask. This purple outline here is the gap in the solder mask between the mask and the pin, and actually would be what is on the board here. And that gap is too small, but I think most manufacturers will actually do less than 10 mil, so we're probably okay there. But again, you check your manufacturer and you come back and double check that that's okay. So now that we've decided that we're good for a design rule, now we actually want to generate our files. And now the files are what are going to be used to upload to manufacturers such as JLC, PCBWay, Advanced Circuits, Technique PCB. What else are there? There's a company, what's the name in Canada or in the States that makes purple PCBs. I forget the name off the top of my head. Osh Park PCB. Thank you. That they make their thing is all about purple PCBs, and they're more expensive, but they have a faster turnaround time. A lot of the time, you'll have an issue of turnaround time is going to be the main thing. Most PCB manufacturers are about the same price range. For a small little PCB like this, that we only need, generally you can have to order at least 5 copies of your PCB. They won't do a run of just one. They're going to give you at least 5, but it's going to be like $2 for 5 PCBs. But then the shipping is going to be maybe $20 to $30 for that. So makes sense to order. If you have multiple PCBs, order them all at the same time. So other thing, maybe I'll just say one last thing before we export this, is maybe you want to put some writing on the board. You can do that by clicking this A in the corner here for text. By default, it gives you a string, which is actually on the top layer of copper, but we don't really want that. We want the top overlay. So we're going to change the layer to top overlay, which is the yellow, the bright yellow. And then we can title the board, put some writing on it, UMIEEE counter and timer. There we go. Now we title our board, so we know what's going on here. And we could put 9-volt power by the power port here. And like Navjot had asked earlier, in this case, we actually probably would have enough space to print all the values on our PCB for the resistors and the capacitors. But generally, you wouldn't do that because you won't have enough space. Like for example, if we go back to this board here, by no means do we have enough space to put, all of the, zoom in here. For example, here with these very, tightly packed resistors, capacitors in this case, we wouldn't have enough space to put all that. Like if I look at the 3D view here, if there's not enough space between all the vias to put those that writing there. And something else to keep in mind when you're putting writing on your board is if you put writing over a via or a through hole, because there's physically, you know, a hole there, and as well as solder that is copper that's being laid on the board, you are going to lose the solder mask there. So I don't know if I did a good enough job here and took care of that, but I'm sure there's something here where there's probably some solder mask or some writing here that has gotten obscured, but that's what happens when you have the silk screen on the board that goes over a hole, is it just gets kind of wiped out. But okay, I will generate our files here. So we want to go File, Fabrication Outputs. First thing we want to do is Gerber files. Gerber files are the files that actually show give the manufacturer the different layers that you have. Inches, 2 to 3 format is the lowest resolution, generally good enough for most boards. 1 mil resolution, like it says here, and that's for us, that's fine. Okay, layers. These are the layers that we're actually sending to them. Generally, I will put top overlay, top paste, top solder, top layer, and the same for the bottom, and we're going to send that to them. And something that I actually have forgotten to do here, and I'm going to go over this for a second, is one thing that you kind of have to do is you have to send them a board outline. And that's, I believe that there's actually a, sometimes there's a layer actually for that. Keep out layer is one of them. Let's just say we're going to use where's one layer I can do? Some of these might have, let's use mechanical 13 for our, that's the, okay, mechanical 1. Let's use that for our board outline here. We're just going to draw a trace around, I'm doing a little bit crudely here, but we're going to draw, essentially you draw a trace around the outline of your board, and that essentially tells the manufacturers where to cut the piece of dielectric board that to cut the piece of dielectric board that actually is going to make up your PCB. So maybe do that a little more carefully. Get the idea. So once again, we're going to make our Gerber files. Let's set up into layers here and put in all our layers. So the bottom layer is the copper. The solder is the pads, those where it has the silver areas around the pads. That's the solder. The paste is not 100% necessary, but I put it in anyways. And the overlay is your silk screen. We want to put in mechanical 1 because that's our board outline. Other stuff, don't worry about it. Okay. Takes a second. And then we have our outputs. Whenever you generate a Gerber file, it gives you this Camtastic file. We don't need that, and we can close that. That's not required. The other set of files that you need for to fabricate your board are drill files and NC drill files. And those are what tells the manufacturer where to drill for the through holes and the pads, or not the pads, but the through holes and your mounting holes, etc. Again, you can set that to 2, 3, leave everything else, and hit OK. Once again, you get a Camtastic file that we don't need. Close that. These files then go to, we go here, I believe they're in here. Okay, they should be in here now. Okay, so now we have our UMIEEE tutorial folder, and you can see here, this is our bottom layer Gerber, overlay Gerber, paste mask Gerber, bottom solder mask Gerber, etc. And we also have our drill report file, this .drr file. So you'd put this file and then all the layer files into a zip file, and then send it off to your manufacturer and upload it to the site of whatever manufacturer you have. And that essentially is how you make the PCB. And then you'd order it from them, set up settings on their site. And many of them, for example, JLC PCB has like a visualizer on their site, so you can just at least double check that you've uploaded the right thing, that everything is there, and you can see what the PCB would look like. You can set the solder mask color, you can set the overlay color, and a number of other different variables as well when you order your board, many of which are fairly self-explanatory once you've designed your PCB, you know what those are, other than, like I said, the copper weight, which is most normally 1 ounce. But other than that, I know I've gone a little over time here. I think that pretty much wraps it up. I don't know if I have anything else here. Oh yes, questions. My circuit board design, and we'll send out this PDF as well. But yeah, please, if anybody has any questions, I'm happy to answer, happy to talk. If anybody wants information on slightly more advanced topics or high-speed design stuff, I'm happy to talk about that for a little while. But thank you, everybody, for coming out and for listening. Hopefully you've learned something and can go off and make your great design for whatever you want to do. So thanks again. If there's any questions, I'd be happy to answer them now. Yeah, you're very welcome, everybody. Right. Okay. Well, I have a different PDF here that actually lists off a bunch of them. I'll just bring up here. This is a tutorial document that we use for SAE. So advanced circuits is delivery time here, average. Alberta printed circuits, fast. Cost is higher. Generally, what you'll find is the manufacturers offshore are going to be more expensive. Sorry, are going to be cheaper but take longer. The ones here in North America are going to be more expensive, but they are shorter. So essentially, I would say Advanced Circuits is pretty good, and Osh Park is pretty good. A little more expensive, but they're all pretty good. But I can send you a more comprehensive list than I've got if you later in the sometime. Yeah, you're welcome, everybody. Sure. Yeah, no worries. You're welcome. And a lot of what I've talked about, if for sure, like an Altium license is obviously very expensive, and even if you join one of the design teams at school later in your life, you may want to use that. Altium does make a free version. I believe it's called Circuit Studio, and that's essentially aimed at kind of the hobbyist maker market, and I believe it is free. Yes, Dylan, I can send you that. Just email me or send me your email, and I can send that off to you. There are free options out there for sure. Some of which are, like I said, Altium has, I think, of the free option called Circuit Studio. There's what else? Autodesk Eagle is free for students that you can download through the Autodesk site, and that's a pretty good software. That's actually what this what this circuit here is made in is Autodesk Eagle. It's kind of the red components and green traces. But yeah, there's lots of variety of options out there for you. Well, thanks again, everybody. I see some people are leaving here, but please, if you have any more questions, I'm happy to chat, or if not, then have a good night. Thanks for coming out.